Number 7, I had tried to give you guys a little bit of a hint of where to start on number 7 last class, but it might not have stuck with you. So number 7 says that a container manufacturer is asked to design a closed rectangular shipping crate with a square base. So I'm going to do my best to draw that picture. So it's a rectangular crate that has a square base.
How do you draw your rectangles so good? I literally, mine end up always being like trapezoids.
Well, Notability will draw, if you draw a rectangle, Notability and holds, Notability will do it for you.
Sorry, I mean rectangular prism, like the 3D rectangle.
That practice. Okay, so for this container, it's a rectangular shipping crate that has a square base. So that means for the base, the length and the width will be the same. So I can say, I can label them as both being like X. It looks like we're going to be measuring in feet. You can use whatever variable you want. I'm just going to use X. And then the height is probably different or could be different. So the height I'm going to label as Y. Again, you can use H if you prefer. It's whatever your preference is. The next sentence tells us that the volume is 10 cubic feet. Okay, so if the volume is 10 cubic feet, that means that length times width times height is equal to 10. Or in this case, that would be X times Y, or X squared times Y. So I'm just going sentence by sentence right now and kind of pulling out the information that they're giving me or interpreting the information that they're giving me. The material for the top and the sides costs $2 per square foot. So to make the top and the bottom, sorry, not the top and the bottom, the top and the sides, it's going to cost $2 per square foot. And there are 4 sides. So I'm just trying to draw an arrow to each of those sides. The material for the bottom costs $3 per square foot. Does that picture make sense to everyone? So that's a picture of the rectangular crate that is being constructed. We don't know the dimensions of the crate yet, but we do know that it costs to make the top and the sides $2 per square foot, and the bottom costs $3 per square foot. So like the bottom, if the area of the bottom was 4 square feet, it would cost $12 to make the bottom, right? So you're taking the $3 and then multiplying by the area. Find the dimensions of the box that will minimize the total cost. So we're finding the dimensions of the box that will minimize the total cost. So we are trying to minimize cost, which means our optimization equation is going to be a cost equation. I'm going to use capital C to represent the total cost. That means that this information up here relating to the volume, this is going to be what we think of as our secondary equation. I'm not sure if we're going to need it. We probably are. But that's not our optimization equation. Our optimization equation is this cost equation because we are trying to minimize cost. So to come up, which this is the hardest part of the problem, to come up with our optimization equation, I'm going to go side by side to think about how I would come up with the cost for each side, right? Because the total cost is going to be adding the cost of each side together. And I just mentioned for the bottom, right? If the area of the bottom was 4 square feet, then the cost of making the bottom would be the $3 because you're taking the $3 and then multiplying by the area since it's $3 per square foot. So since we don't actually know what the area of the base is, but we do know the area of the base can be represented by x times x or x squared, right? Length times width. We can represent the cost of the bottom of the box, or they're calling it a crate, by 3x squared. Now the top has the same dimensions. So the area is also represented by x squared, but the top of the box costs $2 per square foot. So that would be represented, that cost would be represented as 2x squared. Are we okay so far?
Yes.
Okay. I'm going to go side by side. You could, I'm sure many of you could do this in kind of one step, but I'm going to think about going side by side to figure out the cost of each of the remaining sides. It's going to cost $2 per square foot for each of those sides. If I think about just this front side, right? The front side it has an area of x times y, right? Length times width. So the cost of that front side would be 2xy. The cost of the side next to it would also be 2xy. The cost of the back side would also be 2xy. And the cost of the last side would also be 2xy. Now, the case of when they would be different is if you were given like a different cost, or if the base weren't square, like if the base was a rectangle where the length and the width weren't equal, then you'd have different dimensions for the side. So you just want to be careful. I'm going to simplify this equation by combining like terms, right? I can combine the 3x squared and the 2x squared and then all of the 2xy's. So that would be 5x squared plus 2468 xy. So our cost equation is our optimization equation. And we want to differentiate our optimization equation, but we can't do that yet because cost right now is written in terms of x and y, two different variables, meaning cost is dependent on the values of x as well as y. So this is where we use our secondary equation to help us rewrite the optimization equation. So I'm going back up to my secondary equation, and it's going to be easiest for me to just solve for y. And then I can go back to my optimization equation, and now I'm allowed to replace the y with 10 over x squared. And we want to simplify that before we try and differentiate. So this x will cancel with one of these x's. We can multiply the 8 times 10. Here, I'll just go this way. So we'll have 5x squared plus 80 over x, which for taking the derivative and us just wanting to be able to use power rule for this specific function, I can write as 80 times x to the negative first. So that's the optimization equation. Highlight. This is the optimization equation that I'm going to differentiate. Does anyone have any questions at this point?
No.
Thanks, Nick. Okay, so for finding C prime of 10x minus 80 times x to the negative second, that's just using power rule on each term. And then we want to rewrite our derivative using algebra, get rid of the negative exponent. And then because we are going to be finding critical values, we want to rewrite that difference as a single fraction. So to get a common denominator, we're going to think about multiplying the 10x by x squared over x squared, where we get 10x cubed minus 80 in the numerator and x squared in the denominator. Okay, this is algebra we've been using all year. Okay, so then we're going to set the numerator equal to 0. Here's where we're trying to solve for the possible critical values. We're still going to have to think about the constraints on our optimization equation, or in other words, what the domain is for the optimization equation. But this is, I told you guys, I always get to this point where I find the possible critical values, and then I think about what the constraints are. If you want to think about the constraints earlier, like when you write your optimization equation, then great. Okay, so solving that first equation, if we add 80 to both sides, divide by 10, we'll get x cubed equals to 8. Which means x is equal to positive 2, is a possible critical value. And then the solution to this equation is easy at 0, right? So going back up to the picture, I think, okay, well, x and y should both be greater than 0, right? It would be tough to come up with a maximum value for x and y with the given information, but we could say x and y have to be greater than 0. Looking at our optimization equation that's in terms of x, we know that because we have x in the denominator, x can't be 0. So we couldn't say x is greater than or equal to 0. We have to go with strictly greater than 0. So I'm going to state it up here. Y also has to be greater than 0. So thinking about that, that's going to allow us to throw the 0 out as a critical value, but we will want to think about using 0 as an endpoint. 2 will work as a critical value. We don't have our function, our optimization equation defined on a closed interval. Therefore, we're going to have to use the first derivative test. Where we make our analysis line, we put our critical value of 2 on the analysis line, and then I'm going to put 0 as an endpoint. But before I choose my test values, does anyone have any questions about?
So you typically use the first, sorry, it's very noisy here. You typically use the first derivative test, like when you can't use your absolute extrema.
Well,
what's it called?
when you can't apply the extreme value theorem. So
okay.
If your optimization equation can't be defined on a closed interval. And that's
Mhm.
often going to happen when our optimization equation is not a polynomial.
Okay.
So like this is not a polynomial, right? It's actually a rational function. In that case, where we don't have a closed interval to define our optimization equation on, we can't use the implications of extreme value theorem, and therefore we would have to use the first derivative test, but you still have to think about what the constraints are on your optimization equation. And just to go back to Trevor asked that really good question last week, and I'm meeting with Mr. Green today, actually, H period, to just go over and make sure like what the expectations are. If you did have the option of using extreme value theorem, but you chose to use the first derivative test, like what would be needed to make that rigorous enough of proof for an absolute max or min. So the reason we are using the first derivative test is because for our cost equation, we are only able to say x has to be strictly greater than 0, which is an open interval.
Would we ever like have to use in a certain problem, like the second derivative test or whatnot?
No, it's kind of like instead of if you prefer second derivative test over the first derivative test, however, finding the second derivative of this function, like, and you already have the first derivative for finding the critical values anyways, it's just more efficient to use the test. But you technically could, no, that's a good question. You technically could use the second derivative test.
Cool. That's what the textbook does. And it was really confusing.
They use the second derivative test?
Yeah. And it felt like they didn't really need to, but that was that answers my question.
Was it for the one that's is there one that's similar to this? Oh yes, here it is.
Yeah, it's a little similar. I think they use the second derivative from what I looked at.
It would take me a second to look at it. Yeah, I would just, my suggestion is to use the first derivative test just because you're having to find critical values anyways. So I'm going to use 1 and 3 as my test values. And remember, we're plugging test values into the derivative. So like C prime of 1, if I plugged 1 into the derivative, would end up being 10 minus 80, which would be negative, right? Negative is decreasing. And then C prime of 3 ends up being positive, I'm pretty sure. So 10 times 3 minus 80 divided by, oops, accidentally cleared it. 10 times 3 minus 80 divided by 3 squared. You get 190 over 9. Is that right? Yeah. So positive, meaning the graph will change to be increasing. So this is enough work for me for this class. Any of you taking AP next year or future calculus classes, you might have to actually write down a statement that justifies x equals to 2 being the location of an absolute minimum. Because remember, first derivative test allows us to locate local extrema, local max, local mins. But if we do that extra step of analysis, where the domain of our optimization equation, the cost equation, is from 0 to infinity. So if the graph for our cost equation is just from 0 to infinity, and it goes decreasing, 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 and then at x equals to 2 changes to be increasing all the way to infinity, x equals to 2 is going to be the lowest point on the graph. making it the location of the absolute minimum. The question, so going back to what the actual question is asking, is the question saying find the dimensions of the box that will minimize the cost. So it's not asking for the actual minimum cost. Some questions will ask that. It's asking for the dimensions. So thinking about what X represents, that means that the length and the width of the shipping crate are going to be 2 feet. And then we need to figure out what the height of the crate would be by coming back up to our equation where Y is solved for, our secondary equation, because we need the height. So plugging 2 in for X in that equation, that's 10/4, which is 5/2 or 2.5 feet. So the length and the width would need to be 2 feet to minimize costs, and the height would need to be 2.5 feet. Is everyone still with me? Okay, so to minimize, the cost of the shipping crate the width and length must be 2 feet and the height must be 2.5 feet. That summary is pretty specific. I know the answer in the textbook just gives the dimensions like length by width by height, 2 feet by 2 feet by 2.5 feet. That's fine. I'll take that. I just think it's a little bit better to be more specific, but that's fine. If you were to say 2 feet by 2 feet by 2.5 feet. Does anyone have any remaining questions on number 7? Any part? Okay, so I'm going to stop recording.